Chemical bonding 7. Giant covalent structures. The essential idea here is the Lewis structures show electron domains in valence shells and are used to predict molecular shapes. And we're going to predict, or we'll see, the shapes of some carbon allotropes. The nature of science is again using models as representations of the real world. Right, we're going to look at giant covalent versus molecular covalent substances. Some group 14 elements form giant covalent lattice structures instead of molecular structures. And you can see the lattice structure over here of diamond. Compared with the molecular substances, water, methane, and say caffeine down here, you can see these here are separate. There's no chemical bond between them. In fact, we know what kind of bond exists between these. It's hydrogen bonds. And yet there appears to be chemical bonds throughout the whole of this lattice structure. Molecular covalent substances, their structural features. The smallest particle is the covalent molecule. And I'm just going to circle one. There we go. And you can see it's repeated. There's several of them here. Okay. And it can be polar or non-polar, as we know. The attractive forces between particles are intermolecular forces, and they can be dispersion or London forces, dipole-dipole forces, or hydrogen bonds. And the particles arrange themselves, it's rather variable, and it depends on which state they're in. So at room temperature, they can be either solid, liquid, or gas. And this just depends on the strength of the intermolecular forces. Methane over there would be a gas at room temperature because of the weak forces, the weak London forces that hold it together. Conversely, giant covalent substances, their structural features here are, well, the smallest particle is just an atom, and you can see it's an atom here is just being repeated throughout the structure of throughout the lattice structure. The attractive forces between particles, or the atoms, are covalent bonds. And we have regular lattice structures for the arrangement of particles, and at room temperature they are solids. Carbon and silicon form giant covalent network solids. A carbon allotrope is seen above there, and you may not have heard the word allotrope before. It just means different physical forms of an element. So the allotropes of carbon are diamond, graphite, graphene, the carbon-60 are fullerenes, and coal. Here you can see silicon and silicon dioxide, which both are giant covalent networks, solids. Is silicon oxide an allotrope of silicon? What do you think? Well, up here it says different physical forms of an element. So silicon oxide has two elements there, and so it's not considered an allotrope. So let's have a look at the first allotrope of carbon. Diamond. It's a girl's best friend, apparently. The smallest particle is a carbon atom. Each carbon atom is covalently bonded to 4 other carbon atoms. And the arrangement around each carbon atom is tetrahedral. I'm just going to draw on top of this bit here, so you can see the tetrahedron. The bond angle is 109.5, as we know already in a tetrahedral structure when there's no free lone pairs. And the carbon shows sp3 hybridization. The properties of diamond. The structure is very stable due to the strong covalent bonds and tetrahedral atom arrangement. Diamond is not brittle. In fact, it's the hardest known naturally occurring substance in the world. And diamonds will not conduct electricity because there are no freely mobile electrons or charged particles in the solid that can move around. Graphite, the second carbon allotrope. The smallest particle again is just a carbon atom. And each carbon is covalently bonded to 3 other carbon atoms. Carbons are arranged in hexagon rings, which then form sheets. You can see the sheets here, and they just are one on top of another. And you can see the hexagon rings here. This here is a top side view, like down there. The arrangement around each carbon atom is trigonal planar with a bond angle of 120 degrees. The carbon atoms show sp2 hybridization. And it's London dispersion forces which hold these sheets together. So these sheets are held together with London dispersion forces. Properties of graphite. The weak dispersion forces between graphite sheets are easily broken and accounts for some of these properties. Graphite's very brittle. Graphite's slippery. The layers slide over each other easily. This is very useful in pencils and as a machinery lubricant. Graphite will conduct electricity because of the delocalized electrons in the double carbon-carbon bonds. Electrons can move around the carbon atoms inside a plane. So the electrons move between the planes, like so. Okay, carbon allotrope number 3, the structure of graphene. Graphene is made of planar sheets of carbon atoms. It's only 1 atom thick. The smallest particle is a carbon atom, and each carbon atom is covalently bonded to 3 other carbon atoms. Carbon atoms are arranged in hexagonal rings to form a planar sheet. Again, only 1 atom thick. The arrangement around each carbon atom is trigonal planar. The bond angle is 120 degrees, and the carbon atoms show sp2 hybridization. There's your 120 degrees there. Okay. The properties of graphene. Well, it's quite something. Graphene is flexible and it is transparent. It's 200 times stronger than steel. It's thin. It's 1,000,000 times thinner than a human hair. Highly conductive. It's stretchable and it is impermeable. It is amazing. I'd like you all to watch this YouTube clip. I can't embed it because I would get into trouble if I did. So please press stop and watch that YouTube clip now. Okay, carbon allotrope 4. Fullerenes are buckyballs. They look like tiny little footballs. The discovery of fullerenes opened up the field of nanotechnology. The smallest particle in a carbon atom is a carbon atom, and there are 60 carbon atoms in the carbon 60 fullerene. That's why it has 60 in the name of it. Each carbon atom is covalently bonded to 3 other carbon atoms, and the carbon atoms are arranged in pentagonal and hexagonal rings. So pentagonal and hexagonal rings. You can see the pentagonal one facing us just there, and then there's a hexagonal one just there. The arrangement around each carbon atom is trigonal planar. Bond angle of 120 degrees. The carbon atoms show sp2 hybridization. The properties of fullerenes. Fullerenes are poor conductors of electricity. Even though they are delocalized electrons within the molecules, the electrons do not move from one molecule to another. Fullerenes have many possible applications. Look some of these up or read the article that's posted on Moodle. What is the most intriguing application for you? Okay, elemental silicon. Its structure. Silicon, like carbon, is in group 14. Silicon can form a giant covalent solid, much like a diamond. The smallest particle this time, though, is obviously a silicon atom. Each silicon atom is covalently bonded to 4 other silicon atoms. The arrangement around each silicon atom is tetrahedral. I'll show you that. 1, boom, boom. There we go, tetrahedral. The bond angle of 109.5 again, and you should be starting, this should be starting to sink in. You should know that tetrahedral structures have an angle of 109.5, and the silicon atoms show sp3 hybridization. The properties, you probably already know some of the properties. It's a semiconductor of electricity. It has a high melting point, but it is less than that of diamond or carbon. Can you think of a reason for this? Yes, that's right. It's because the carbon-carbon bonds are stronger than the silicon-silicon bonds. More energy is required to break the carbon-carbon bonds. Silicon dioxide structure. The formula for silicon dioxide is SiO2. It makes many think it is made of molecules, but it isn't. The formula SiO2 refers to the ratio of atoms present in the lattice structure. Okay. The smallest particles are silicon and oxygen atoms. 1 silicon, 2 oxygen atoms. Each silicon atom is covalently bonded to 4 oxygen atoms, and each oxygen atom is covalently bonded to 2 silicon atoms. The arrangement around each silicon atom is tetrahedral, with a bond angle, that's right, 109.5, and both silicon and oxygen atoms show sp3 hybridization. Silicon dioxide, its properties. Silicon dioxide is insoluble in water, which is good for us because the beach would not be much fun if it were soluble. It has a high melting point. Again, you wouldn't want sand to turn into liquid whilst you were sunbathing. A poor conductor of heat and electricity, as it has no free electrons to move around. That's it for this video. I'm just going to add one more thing, and that's a picture of me riding one of those giant sandworms from the popular science fiction book Dune. And whilst in battle, I will yell an important message.